And recording. Okay, so today what we're going to talk about a bit, is when we have these situations where we have higher order polynomials. So a polynomial to the 6th degree has a variable to the 6th power in it. That's how we know the degree of a variable. It's going to look something like this. It may have a different form, but you're going to end up with some really weird looking polynomials. We just got to know what we're looking for with it. The three main things we're looking for, we're figuring out information about the end behavior. As it goes towards negative infinity with x, does f of x, our y value, go up or down? Does f of x go to negative infinity or up towards positive infinity? Because this arrow denotes that it keeps going down and down and down and down forever. Other end behavior over here, as x approaches positive infinity, what happens to f of x? In this case, f of x goes up towards positive infinity. It keeps going up forever. So we have end behavior. We have turning points, where you can think of this as a roller coaster. You know, it's tick, 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 and then it finally changes direction, goes down. Turning points are just every time the slope, the increasing or decreasing, changes. Okay. So if this was a stock, you know, you can use these higher order functions to understand the stock market and see the trends in the stock market, and actually even plot the exact points and create your higher order polynomial from the actual stocks to make some predictions. So if you bought it here, you know, at $1, you get up to this point, maybe it's at, you know, $3. That's when you'd want to sell it before it starts to reduce in value, and it may even go lower than your initial investment. So the turning points are what we pay attention to if you're looking at finance with stocks. You look to see what these troughs, specifically the troughs, are really important for that. Why is this the relative maximum? First off, if I just called this a maximum, could that be confusing? Yeah. Why could it be confusing? Because what? There's higher points. There's other maximums, right? Here's a maximum, here's a maximum. And in the situation where if they were exactly the same height, it would be really confusing because there's like two maximums that are the same. So relative maximum just means relative to this side of the function, this side of the graph, that's the relative maximum. Over here, this is a relative maximum. This isn't even close to this relative minimum, but that's a relative minimum, and so is this. This is a relative minimum. So basically, we have end behaviors. We have the turning points, which also are the places of our minimum and maximum relatives. And then we have roots. The roots are right here where f of x equal to 0. We have some value for x along those routes. So we're basically going to, from two key pieces of information, we're going to be able to figure out all this. Okay, so there's two things to really get down first, and then all that will come together. So let's look at this. This is one key part. The degree of the polynomial, the highest term is your degree, and that's n. So way over here when we get to this, what's the degree of this polynomial? 7. Look, it's the 3x to the 7. The highest degree is your power of your polynomial. Also, polynomials have to have a whole number exponent, and they have to extend positive infinity and negative infinity as far as their x values go. They have to keep going out. Okay? And even if something goes up, it's still going out. It just keeps going up. Right? So with this, if we had something to the 1/2, or we had a root isn't a polynomial, because by definition, a square root starts at 0. You can't have any negatives in a square root. So this isn't a pure polynomial. It's more of a relation. Okay. So, well, it's still a function. It's just not polynomial per se. Now, the three things we're going to figure out have to do with the n value and the a value. So first off, there's some ways to remember this. I'll just remind you from last year. What kind of shape does this graph create? Remember from last year? Parabola, right? And this letter out front, a is always the coefficient out front of the highest term. A is outside of x squared because x squared is the highest term here. And when a was positive, what did we see? Is what? Yeah. Look like this, right? So when A is positive, it's happy face, opens up. What happens when A is negative? Sad face. Implicit within this, is there a minimum or a maximum with this? Minimum. Minimum. Is this a minimum or a maximum? Maximum. So it's kind of one of those situations where you know if A is positive or negative, it gives you all the other information within it. I want you to kind of build this information from these 4 boxes in a similar way. I'll keep this up for a second. But looking at this, in behavior is as x approaches positive infinity or negative infinity, just like what happens on the sides. That's all we're talking about. All right. So first off, box 1 and 2. Box 1 and 2. Does this quadratic that I wrote over here, does it, I'll even change it. Let's make it 2x plus, or 2x squared plus 2x plus 1. Do boxes 1 and 2 apply to this problem right here? Read what the conditions are. If what? N, that's our degree, is even, right? Boxes 1 and 2 have, if n is even. Is n even right here? N is 2, right? N is equal to 2, it's even. That's going to be one of the key information to pull out. The other key information is A positive or negative. You see it, it's in every single one of these. A, is it positive or negative? Yeah, A is positive. So because we have n of 2 and A is positive, I look over here and what does it say? Both ends up towards the positive infinity. So if you think of it from last year, what we learned with if A is positive, happy face, if A is negative, sad face, it kind of works with the same process because last year we only had exponent of 2. Let's get back to this. All right. So all we need to do is find our n value, find our a value, and match them up to see what is going to happen at the end of these functions. So help me out with this. What is my n value for this one? 3. What's my a value? 1. So it's positive. So we have a positive. We have a 3, which is an odd number. So just with your neighbor 5 seconds, which of those boxes applies to example number 1? Is it box 1, 2, 3, or 4? Got it? Exponent 3. Odd. All right. Okay, which box? I hear 3. 3. Because you know in the highest term is 3, which is odd. A is 1 because there's a 1 in front of this x to the 3rd power. So 1. Or at least in the least you can see it's positive. So odd, positive, odd, positive. Now watch, this is how I'm going to write it. As x approaches positive infinity, so as x approaches positive infinity off to the right side, what happens with f of x, our y values, up or down? What do you say? As x approaches positive infinity, f of x approaches positive infinity. If I was writing this all the way out, I'd say, as x approaches positive infinity, that's what happens to f of x. As x approaches negative infinity, f of x approaches negative infinity. So you see, you can see what happens as far as x goes, what happens with your y. This first one's the hardest one to grasp because it has 4 different options. Okay, but you find your n, you find your a, you can work it out from there. I want you to go ahead and do this one on your own. I'll give you a minute to work on this. Check with your neighbor when you're done. Start out. What's your n value? What's your a value? Work that out. Go ahead and see if you can figure what's happening as x approaches negative infinity this time. All right, now double check with your neighbor. Double check they have it done. It's Maybe decide with your neighbor which box you're looking at. That's what we'll need to know. Negatives. Okay. What's our in value for this? What degree term is it? Or what degree polynomial? 5. So we know it's odd. How about our a value? -6. We're negative, odd negative. And then from there we could figure out, we're trying to figure out when x goes to negative infinity, what's happening. It's going to go up towards positive. That's all you need to know. So if I was trying to write this and I was starting this out, I would know that, well, I'll do this one up here. I would know that as x approaches negative infinity, it goes down, so this way. And as x approaches positive infinity, it goes up. So I know that at least that's the way the graph's going to end in some way. All right. The other two are really straightforward. Really straightforward. You know what the turning point is now on the roller coaster ride. So with this, the turning points, the number of turning points, max, is just whatever your in value is minus 1. And that's the max number of turning points. They may not all be used up, but that's the max. Okay, so we call that the relative min, the relative max, just because there might be more than one relative, each one. And the last bit, roots. Whatever your in value is, that's also the maximum number of roots. That's the maximum number of times you can cross the x-axis. Okay. So what we're going to do is sketch this up here. I want you to go ahead and fill in for, yeah, that might do. Tell me what the n is. Tell me what the a is. What happens as x approaches positive infinity? As x approaches negative infinity. So really I should just say f of x approaches what? F of x approaches what? And then from there, how about the, so this is in behavior. Turning points, give me a number. Roots, real roots, give me a number. That's enough to graph it. Almost. Step 4, you can also plug in 0. We'll do that together. Start with that stuff. So, in the biggest exponent you see up here? 7. And then go to A, that's always that coefficient out in front, the number in front of the variable. Okay, if you're not sure where to look, these first two bits of information, I know this is the 7th because it's to the 7th power. I know that this is 3 because this is the coefficient of the leading term. So we have odd and we have positive. Odd, positive. So which one of our boxes did that fit into? 1, 2, 3, or 4? What do you say? Odd, positive, right? So as it approaches negative infinity, we get to, we start going towards negative infinity. It looks like towards positive is positive. So you see we have our in behavior step. Number of turning points, I'm just going to go in minus 1. Yeah. 7 minus 1, 6. And this is 6 max. Remember that you may not use all 6 turning points, but it could have up to 6. Okay. All right. And then lastly, number of roots. 7. Because n is 7, that's the number of maximum roots. May not use all those. Okay. So if I'm graphing this, I want to find in behavior, turning points, real roots. Plug in 0 for x to see where that y-intercept is. That's not hard. Watch. Plug in 0 here. What happens to the term? Cancels. It's 0. Here, 0. Here, 0. What's left? The y-intercept is equal to 4. So already I know I can go 1, 2, 3, 4. That's my y-intercept. Let's see, and I know it goes up this way, down that way. Okay. It may have up to 7 roots, and may have up to 7 or 6 max. So old school, before Desmos, or it seems like at a certain point, everyone was okay with using technology, and that's just, it's ubiquitous with our society, so it's fine. Here is the graph now we'll look at. With Desmos, remember, if you get zoomed in and you're in a weird spot, you don't even know where you are compared to the origin, just push the default zoom, the home button, and then you could see everything again. You could change the window, you can do a lot of things with the toolbar up here. So one thing I want to point out is that when you use Desmos, you just click on it, and it brings up all the important turning points. Here's the relative min and max, and here is the... You guys are lit. That's great. How long was that going to last? Explaining something, the doors closed. All right, so relative minimum at this point, relative max. Here was our y-intercept of 4. Here at negative 0.779 and 0, that's our 1 root. So we could have had 7 roots, but there's only 1. There's really no way to know until you start to graph it. So you could have done this with a table to graph a bunch of points, but at this point, step 5 is going to use technology to see the full shape. So it kind of looks like this. Okay. It's good practice. You might label these minimum and max, relative max, with the point, relative min, with the point. Here's the root, point. You could do all that. That would be a good labeling of this. Okay. It actually, as you get started, so that is over there. It's hard to see. All right, I feel like you have to do some of these problems. First, I'll give you one thing that will come up. They're going to just give you a graph like this and say, what is the highest degree that you could have without any other information? So what can we see here first off? We could see what? Turning points. We have 1 turning point, 2, 3, 4. So my turning point is 4. There's 4 of them. Now we have to remember that turning point is equal to n minus 1. So how could I find my n value, the maximum? Add 1. Good. If you can't see that quite yet, you can know that turning point is n minus 1. In this case, that was equal to 4, so you would just add 1. So your n is 5. That's the max that you could have for this one. So we could say this is the 5th. It's a 5th degree. And then we can make up some other things from that. Yes?
How do we know that they're using the maximum turning points?
Oh, one more time, the maximum what?
The max amount of turning points.
Oh, got it. You won't know until you start to graph it. So what I'd say here is, well, in the other direction you'll see, sometimes you have to say it's going to be, less or equal to 4. So sometimes you're going to express it as an inequality. I don't know if we hit that for this homework, but we may. Okay. There's just one problem like this. I want you to be able to go the other direction. So I think we can knock that out. I think we'll be okay with that. Let's go ahead and make this the